Hello, I'm Patrick Mercier from the University of California, San Diego. I'm here to present physiochemical interface circuits for wearable and implantable sensing systems. I'm a professor at UCSD. My research interests are in biomedical circuits, RFICs, power management ICs, mixed signal circuits, and a collection of other areas. I'm a member of the ISSCC Technical Program Committee and a few others and other journals. And this year I was invited to give a tutorial at ISSCC 2020, and this video is very much a abridged version of that tutorial. Now, just a few notes before we get started. There's a PDF version of this mini tutorial is available online, and SSCS members can view a bunch of other tutorials online at the links provided here, as well as past webinars and so on. So let's get into the main topic today, which is wearable and implantable systems. There's lots of excitement and lots of really interesting opportunities in this space. We look at devices like wearable cardiac monitoring systems. We look at devices like brain-computer interfaces, and even things like artificial pancreases that measure blood sugar levels and deliver insulin in response for diabetic patients. We can also think about devices outside of the use of humans for livestock monitoring and veterinarian applications as well. So there's a lot of really good excitement in these areas, and yet there are still a number of major design challenges. So what I'd like to focus on for the next few moments is specifically on the design of wearable systems. So wearables have a lot of excitement. There's a lot of good revenue streams being generated in the wearables marketplace. But if we look to the future of wearables, we're still not really where I think we ought to be. And if I could summarize in one picture why I think we're not where we need to be, I would choose a picture like this. This person is clearly not happy with their wearables. There's many challenges here. So how do we address these? What are the challenges? Number one, a lot of these devices are too big. They don't seamlessly integrate into daily life. Number two is battery life. A lot of these devices have rather poor battery lives, and that's okay if you're wearing a smartwatch and you only have to recharge that one device every day. But as we move forward to generating or to having lots of different wearable devices, users will simply not tolerate charging a handful of devices every day. It's too large of a use case friction, and people aren't going to do it. So we need to address this. And last, but certainly not least, these devices have to do something useful. Okay, so I have a smartwatch. It tracks the number of steps I take, but I don't go to my doctor and say, hey, look, doc, I walked 10,000 steps today. What's my prognosis? The doctor just doesn't care. That's not useful information to improve your healthcare outcomes, or not totally useful information to improve your healthcare outcomes. What we need are to develop new sensor technologies that give us access to more rich information about the physiology of the human in order to help improve our ability to deliver good advice, deliver good therapies, and so on. So the objective of this tutorial is to understand the fundamentals of how to build low power, low noise biointerface circuits towards making devices so unobtrusive that the user is virtually unaware that they're wearing their wearable. So I call this unawearables, and that's really what we're going for today. Now, if we look at today's marketplace, the wearables market is roughly divided into two classes of devices. There's devices that measure physical attributes, motion, temperature, respiration, so on. We'd love to do blood pressure, by the way, but it's very difficult to do well, without a cuff, that is. And electrical devices that measure ECG, EEG, and so on. So this is, these are good areas to be working on, but there's a really big, important piece of the pie here that's missing. When you go to the doctor, what do? They take your weight, they take your blood pressure, and then they send you down to get blood drawn, to do lab work. Okay, and this is just totally missing from this picture. So that's an opportunity for us as researchers and developers to say, how can we add biochemical sensing attributes to, for example, some of these wearable devices? If we can do this, this will create much richer information, much richer data sets that will allow clinicians, that will allow athletes and the general population to make much more informed decisions about therapy, about training regimens, and so on. So most of the commercially available devices are in this physical domain. There's certainly some commercially available devices on electrophysiology as well. They're not as large of a marketplace, at least not today. And so the focus of the tutorial I gave at ISSCC 2020 was on both the electrophysiology and the physiochemistry. The focus of today's short mini tutorial video is going to be on the physiochemistry side of things. So if you look at how we do chemical sensing today, well, we draw blood. We send it to the lab where it's analyzed by large benchtop instruments. This is expensive, it's painful, and perhaps most importantly, it doesn't happen very often. Many of us only get our blood analyzed maybe once a year at our annual physical. Many of us don't go to our annual physical and don't get this done. Okay, so we are taking very infrequent spot measurements. I can assure you that the human body changes far more rapidly than once per year. We are undersampling. Our Nyquist rate is much faster than once per year. We need to do a better job here. To that end, researchers have been developing things like point-of-care devices. These are devices where you can do the measurements at home and so on. But these devices typically need, either some blood drawn or a urine sample or a saliva sample or something like this. And so it's still a spot measurement. We're not taking a continuous measurement with these devices. It's a step in the right direction, but we'd like to take it one step further. So what we really need is a ideally non-invasive device that can do continuous real-time measurements of physiochemical parameters. Now, there are obvious medical applications for this sort of technology. There's also non-medical applications, for example, in athletics and wellness applications. I've personally had many conversations with the US Olympic Committee, with Tour de France cyclists, with National Football League players about measuring lactate levels. Lactate is an important biomarker that indicates the exertion level of the athlete. High-end athletes really want to be able to monitor this in order to help them train optimally. Current state-of-the-art technologies to measure lactate involve stopping your workout, pricking your finger, drawing a little bit of blood, bringing that blood close to this lactate monitoring system, waiting 30 seconds, and then getting your result. This is decidedly not on a wearable, and this is not something athletes want to do when they are training. So again, what we need are non-invasive or continuous sensing modalities. So it turns out that a good way to do this, there's many possible ways to do chemical monitoring. Probably the best way, at least on the marketplace today, is through electrochemical biosensors. Chemicals and the body communicate information via ionic current flow, whereas electronics use electrons, right? And so we need to somehow convert between ionics and electronics in order to access chemical information. We do this, in this case, through electrochemical biosensors that can be categorized in one of three different categories. We have potentiometric biosensors, which effectively measure open circuit voltages. We have amperemetric biosensors, which effectively measure currents through redox reactions. And we have electrochemical impedance spectroscopy sensors, which effectively measure complex impedances over a wide variety of frequencies. So all of these measurements, voltage, current, or complex impedance, ideally, if the sensor is designed correctly, are proportional to the chemical analyte that we are trying to measure. Okay, so that's really the objective. Now, as I mentioned, there's other ways to do this using optical techniques, millimeter wave, ultrasound, and so on. But the difficulty with those techniques is that they don't typically offer very good specificity. So if you want to do measurements in complex fluids where there's many other analytes present, like in human blood, sweat, tears, etc., those are difficult. It's still very much a work in progress, whereas electrochemical sensors have built-in specificity, as we'll discuss momentarily. These biosensors can be fabricated on a number of different platform technologies. We can manufacture them on plastics. You may have heard of the Google contact lens project, for example, although for various reasons that project didn't continue, but the core technology is still very relevant today. We can fabricate on textiles, temporary tattoos. Recently, we've been doing a lot of work on microneedle-based platforms and so on. The key idea here is we somehow modify the surface of the working electrode of such a system such that imparts selectivity towards a specific analyte. So let's take a look at the circuit interface requirements for two of these different types of biosensor technologies. We'll start with potentiometric biosensors. Again, these measure the voltage between a working electrode and a reference electrode. The reference electrode can be placed in solution. It's silver chloride, something like this. The working electrode is coated with an ion-selective membrane. Just as the name implies, this is a membrane that allows ions of a specific type to pass through, which we can then measure through effectively just an open circuit measurement. The ion-selective membrane is engineered for specific ion types. We can measure things like pH, sodium, potassium, chloride, etc. Since it's just an open circuit measurement, we effectively just need, a high impedance amplifier. Very high input impedance. Voltage range is somewhere between 0 and 400 millivolts typically. Noise has to be down to the microvolt regime, and the bandwidth can be relatively low. These are not high frequency measurements that we need to take. So these are actually relatively easy to build. It turns out that we don't need to sample ion concentration very rapidly when we're dealing with on-body or in-body measurements. Something like once a minute is probably good enough. So we exploited that in some recent research where we built a potentiometric amplifier, an analog to digital converter, a 2.4 gigahertz transmitter, a DC-DC converter, reference generators, oscillators, everything that we needed to do wireless ion sensing was integrated into an approximately 1 square millimeter chip. And because the sampling rate of the system was low, we could aggressively duty cycle the design and bring down the average currents of the continuously operating blocks very low to the point where the entire system power consumption, including all of the blocks here, which also includes that transmitter, consumed only 5.5 nanowatts of power. That's operating at a sampling rate of 10 samples per second, which is excessive for these sort of applications, but it just demonstrates what we can do at such low powers. So at these low power levels, this really opens up some really interesting new opportunities for us to explore new application spaces. Now, as you can see, the measurements here, which were measured with a sodium selective electrode, show a nice linear near-Nernstian response as we vary the concentration of sodium ions throughout our system. Moving on to the next category of electrochemical sensors, these are amperometric biosensors. These work by coating the working electrode or functionalizing the working electrode with a specific type of enzyme that reacts specifically to the analyte in question. These enzymatic reactions, which eventually cause redox currents to flow, require a fairly precise voltage applied across the electrode in order to get the chemical reaction working optimally. So we do this by applying a known voltage between the reference electrode and the working electrode. However, when we do this, currents are flowing through the system. And as a result, we're going to have IR drops across our electrodes and so on. These IR drops can slightly adjust the actual applied voltage as seen across the working electrode, which can affect the ability of the electrode to function as designed. One solution to this is just make the reference electrode really big, so its impedance is very low, but this is not always practical in a small system. So the typical solution to this problem is to introduce a third electrode into the mix. What we do here is we apply a precise voltage between the working electrode and the reference electrode. but we make the reference electrode a high impedance node in the sense that there's no current that's allowed to flow through it. As a result, we know exactly what that voltage is on the reference electrode, and therefore on the working electrode. But we're applying a voltage across an electrochemical cell, and therefore current wants to flow just like it would in a battery. So we have to have a path for this current to flow. This is where that third electrode comes to play. Through some circuit called a potentiostat, we drive the third electrode, called the counter electrode, to the very specific voltage needed to let the current flow through the system. We do this through a feedback circuit called a potentiostat. So here's an example of a simple potentiostat. There are many possible configurations of potentiostats, but in this case we have our working electrode is grounded. We have a reference electrode, which is connected to some reference voltage supplied by the circuit. And then we have a driving amplifier that drives the output of the counter electrode precisely so that just the right amount of current flows through the electrochemical cell. The requirements for the circuit are that the amplifier needs to have high gain, usually has to have a low input referred offset, low noise, and sufficient bandwidth for operation. There's many different variants of how we can build these potentiostat circuits, but let's go into a case study of what we did for a specific application. This is an example of a hybrid electrophysiology and physiochemistry sensing system. This is actually the very first demonstration of a wearable device that could simultaneously monitor a physiochemical parameter and an electrophysiology parameter at the same time on a freely behaving human subject. What we did is we added 2 electrodes of silver chloride to do ECG measurement, and then we had a 3-electrode electrochemical cell in the middle responsible for measuring lactate, which is something that athletes wanted to get access to. As you can see here, we built the sensor as a temporary tattoo that we then magnetically connected a small circuit board to run the sensor at. And you can see here that we can extract ECG waveforms, we can extract heart rate and heart rate variability from those ECG waveforms, and we can also get access to some lactate measurements. The physical design of this system looks as follows. We have our functionalized working electrode, in this case functionalized with lactate oxidase, that's the enzyme, along with a cocktail of other chemicals to impart stability and so on. And we drive this circuit with a potentiostat. So we drive a specific voltage between the working electrode and the reference electrode, and we have our feedback amplifier driving the counter electrode to facilitate the right amount of current to flow through the electrochemical cell. That current then passes through a transimpedance amplifier, which converts the current into a voltage that then gets digitized by an analog to digital converter. In this particular embodiment, we did some experiments where we varied, say, for example, the lactate concentration, and we could see a fairly linear response of the current output of the system in response to varying lactate concentrations. Next, we added some electrodes for ECG amplification, which we attached to an ECG amplifier. Now, there is a little bit of a challenge here. The potentiostat is a low impedance system that's driving these electrodes to known voltages through low impedance connections. And the ECG instrumentation amplifier is by design a high impedance system that's measuring biopotentials. These electrodes are placed on the skin. The skin has some sweat on it. Sweat is conductive. Skin is conductive for that matter. And so the electrodes are all electrically connected, perhaps loosely, but there's still some impedance between the electrodes. And so if we're not careful, we could potentially have some crosstalk of when we apply potentials to the potentiostat that could disrupt the ECG waveform. A simple solution that we applied here is to apply a hydrophobic coating between the electrochemical cells and the ECG electrodes, and that increased the effective impedance between the electrochemical cells and the ECG electrodes, which attenuated the amount of crosstalk we saw between the devices to the point where we did not observe any measurable crosstalk between these two sensing modalities. So this is a simple way of how to build a wearable on-body electrochemical cell. There are interesting directions on how we can build these to be possibly self-powered. So this is an example work where we found that the electrochemical cell potential of, say, our glucose and our lactate devices also work very well as a biofuel cell. Glucose and lactate are rich biofuel sources of energy, and our biofuel cells can convert this into electricity. And in this example, the voltages generated by these biofuel cells is on the order of, say, 0.2 to 0.4 volts, which, if you're careful, is enough to run a CMOS circuit. So in this particular example, we directly powered an analog to digital converter and a 900 megahertz transmitter directly from the biofuel cell, let's say 0.3 to 0.4 volts, and digitized the maximum power point of this circuit through a time-interleaved maximum power point circuit. The output power of this circuit was linearly proportional to the glucose concentration. The total power consumption of the circuit was about 1 microwatt, 100% of which was powered from the glucose biofuel cell. So this was an example of a glucose-powered glucose cell. If you had attended the full-length tutorial at ISSCC 2020, we would have discussed in-depth electrophysiology, as well as much more details on the physiochemistry side of things, along with a useful list of references. So some of these past conference tutorials are available online at the following links, and the actual conference tutorials are also available online. In addition, there are many member benefits associated with being a member of the Solid State Circuits Society, so we do highly encourage you to join the Society to get access to those benefits. And with that, I would like to conclude my presentation. Thank you for listening.